Today's topic is squeeze theorem or sandwich theorem. So consider a function f that is trapped between two functions L and U. So L is for the lower bound and U is for the upper bound. If we can squeeze the function f of x between two other functions L of x and U of x, both L of x and U of x have the limit defined at point C, then we know the limit L of x, x approaches C, is equal to limit U of x, x approaches C, and our function f of x is squeezed between our function blue function, squeezed between the upper bound function and the lower bound function, L and U function. And we know the limit exists at those for both of those functions at point C, and that limit is equal. Then we can say our function f is squeezed in between or sandwiched in between those two functions, and we can say the limit x approaches c f of x is equal to the same number that limit L x approaches c L of x is and limit x approaches c U of x is. So sandwich theorem it's used to compute the limit of a function where you cannot plug in the limiting x value, for which you cannot. If we can find two functions which are the boundary functions, usually we use it for the trig functions. So if we can squeeze our function in between two values, and we can take the limit from there, and whatever is the limit of the upper bound and the lower bound at point C, that limit is equal, then limit x approaches the f of x will be the same number. Okay, so whatever is the limit at point C for the lower bound function and the upper bound function, f of x will have the same limit. We couldn't compute the limit x approaches c f of x, but because we squeezed it or sandwiched it between those two other functions, the upper bound and lower bound function, and they have the same limit, we can say the limit x approaches c f of x is the same number. All right, let's see some examples of sandwich function or sandwich theorem. So here we want 2 minus x squared less than equals g of x less than equal 2 cosine of x for all x. We're given that the function g of x, we don't know what g of x function is, but it's a function that is in between these two functions. We want to find the limit x approaches 0 g of x. We don't even know what the function g of x is. That's okay. So we're going to go ahead and take the limit x approaches 0 for the entire function. So limit x approaches 0 to cosine of x. When x approaches 0, 2 minus x squared will go to, when x is going to 0, 2 minus x squared will go to 2. And limit x approaches 0 g of x is in the middle. When x approaches 0, 2 cosine of 0. Cosine of 0 is 1. 2 minus 1 is 2. So we can see we were able to squeeze our function in the middle, and the limit of lower bound and upper bound function both go to 2. So we can say limit x goes to 0, g of x is equal to 2. Limit x approaches 0, g of x is equal to 2. See a couple more examples. Here's another example. We have limit x approaches 0, x sine 1 of x equal to 0. Earlier, we saw this in using numerical method. We saw this using graphically. Where is this limit headed? We saw this was an oscillating function. We cannot use the product law here, because in order for the product law to work, both individual limits should exist, and this limit does not exist. Sine 1 of x, x approaches 0, we saw it was the oscillations were getting bigger and we were getting positive and negative values from both sides. This limit does not exist, so we couldn't use the product law. So we're going to go ahead and use the sandwich theorem. We know we can sandwich any trig function. Sine x and cosine x always lie between -1 and +1. We are not able to sandwich any trig function, but sine x and cosine x both stay between -1 and +1. So sine x, sine of any function, sine of 1, sine of x, sine of 1 over x, any function lies between -1 and +1. Now we're going to multiply with x. So -1 times x, x times sine 1 over x, 1 times x. And now we're going to go ahead and take the limit as x approaches 0 everywhere. Limit x approaches 0, negative x. Limit x approaches 0, x sine limit x approaches 0, x. Now, this is going to be 0, because when x approaches 0, the limit of negative x exists, which is equal to 0. and limit x approaches 0, x sine 1 over x, and limit x approaches 0 of x is also equal to 0. So by using sandwich theorem, by using squeeze theorem or sandwich theorem, we can say limit x approaches 0, x times 1 over sine of 1 over x, x times sine of 1 over x is equal to 0. Okay, so we didn't really have any way of evaluating. We saw graphically that when we did x times sine 1 over x, the oscillations were getting smaller and smaller and smaller and smaller as we were getting closer to 0. And we saw it graphically earlier when we were looking at limits. Graphically, we did look at a graph of x times sine 1 over x. So oscillations are getting smaller and smaller as we're getting closer to 0, and this limit turns out to be 0. We also saw that using squeeze theorem. Another example of using squeeze theorem. So another trig function, cosine of 1 over x can be squeezed between 1 and negative 1. Cosine and sine always stay between 1 and negative 1. Now, I'm going to multiply everything with an x square, cosine of 1 over x squared times 1. Now we're going to go ahead and do limit x approaches 0 of negative x squared, limit x approaches 0 of x squared cosine 1 over x, limit x approaches 0 of x squared. So that's going to leave us with limit. We were able to squeeze our limit into the two functions whose limit is equal to 0. So we can say using sandwich theorem or squeeze theorem, limit x approaches 0 of x squared cosine of 1 over x is also equal to 0. And here's a graph of this function. We were able to squeeze it into positive x squared. So we did squeeze it into positive x squared and negative x squared. We were able to squeeze our function into two other functions whose limit is 0 as x approaches 0. Another example of squeeze theorem. So we want to evaluate limit x approaches to x minus 2 sine pi over x minus 2. Again, we don't have any other way of evaluating this limit. We can look at it numerically, we can look at it graphically, but we don't have any algebraic techniques that would work here. So we're going to start by squeezing the sine pi over x minus 2 between 1 and negative 1. Now multiply everything with x minus 2, all three parts of inequality, multiply with x minus 2. Negative 1, I'm not writing times negative 1 here because when you multiply something with 1, that doesn't really matter. Now we're going to go ahead and limit x approaches 2, limit x approaches to x minus 2 sine pi over x minus 2, limit x approaches to x minus 2. We know that these both limits go to 0 when x is approaching 2. So by using squeeze theorem, we can say limit x approaches to x minus 2 sine pi over x minus 2 is equal to 0. That's all for the squeeze limit. Again, our goal is to sandwich our function between two functions whose limit exists at point C, and those two limits are equal. So if those two limits are equal for the lower bound and upper bound function, we can say because our function f is squeezed between two functions at that point C, we can say that f of x has the same limit at point C.